Hello everyone, today's video will focus on the many problems that Mars colonization may face and their solutions. Mars colonization refers to the idea of establishing permanent settlements on Mars by humans. Mars is the planet in the solar system, second only to Earth, that is most suitable for human habitation. Therefore, Mars is the focus of academic research and one of the candidate sets for extraterrestrial colonization. In this process, there are still many problems waiting to be solved at present.
One of the most critical challenges in colonizing Mars is the nature of its soil or regolith. Or it might appear similar to Earth's dirt, Martian soil presents several scientific and practical obstacles that must be addressed to sustain human life and agriculture. Firstly, Martian soil is toxic. It contains perchlorates, which are chemicals that are harmful to humans if ingested or inhaled. On Mars, perchlorates have been found in concentrations up to 0.6% by weight, which is far above safe levels. In the human body, perchlorates block iodine uptake in the thyroid gland, interfering with hormone production. Furthermore, Martian soil is lacking in organic material, the basic nutrients and microbes that Earth plants rely on to grow. Secondly, the soil is extremely dry and lacks nitrogen, a key nutrient for plant life. It also has fine, abrasive dust particles that can damage mechanical parts and pose respiratory risks for humans. To solve these issues, there are few possible innovative solutions. One promising approach is soil detoxification and amendment. Through chemical treatment or the use of specific microbes, perchlorates could be broken down into harmless byproducts. Research on Earth has already shown certain bacteria known as perchlorate-reducing bacteria, PRB, or dissimilatory perchlorate-reducing bacteria, DPRB, which can utilize perchlorate as an electron acceptor during anaerobic respiration, offering a natural way of detoxification. Another method is to use hydroponics or aeroponics, growing plants without soil by delivering nutrients through water or mist. These systems have already been tested in space environment, including the International Space Station, and could bypass the need for Martian soil entirely. Furthermore, a more hybrid approach involves creating Martian greenhouses that use a mixture of Martian regolith and imported Earth compost or synthetic nutrients. This will conserve cargo weight emissions while still supporting plant life. These greenhouses could also help regulate temperature, carbon dioxide, and humidity, creating a stable environment for both plants and humans. Overall, while the Martian soil presents significant challenges, interdisciplinary solutions from biology, chemistry, and engineering offer hope. By detoxifying the soil, using advanced agricultural technologies, and designing sustainable ecosystems, we move one step closer to making Mars a viable home for future generations.
During the process of colonizing Mars, geological and climatic disasters have brought huge challenges. In terms of geology, Mars earthquakes are mainly caused by internal cooling and contraction as well as meteor impact. Because Mars lacks buffer media like the vegetation and soil on Earth, the seismic wave propagation efficiency is high and destructive power is strong. According to the data from InSight, the magnitude 4.2 earthquake is it monitored generated vibration that was sufficient to loosen the foundation of the base buildings and crack the walls. Meanwhile, the dry canyons and riverbeds on the surface of Mars have fragile geological structures, such as the Marno Canyon, which is 4,000 kilometers long and 7 kilometers deep. Earthquakes can easily trigger large-scale rockfalls, threatening the safety of the base. Among climate disasters, the destructive power of global dust storms on Mars is astonishing. The Martian atmosphere is thin but windy, with sand particles ranging from 1 to 10 micrometers. Under the influence of strong winds of 30 to 50 meters per second, it erodes space facilities like sandpaper. In 2018, a global dust storm covered more than two-thirds of the surface area of Mars, causing the power of the Curiosity rover solar panels to drop by over 15%. Moreover, the temperature difference between day and night during the dust storm could reach over 100 degrees Celsius, seriously affecting the base temperatures control system. To this end, multiple measures need to be taken to deal with disasters. To resist earthquakes, the building adopts a flexible seismic structures and modular design and uses shape memory alloys to enhance structural stability. The orbital vehicles is equipped with synthetic aperture radar and multispectral images equipment to draw geological risk maps with a resolution of 0.5 meters and avoid areas with a high incidence of disasters. Deploy earthquake monitors based on quantum sensing technology to issue early warnings and automatically reinforce buildings. To deal with dust storm, solar panels apply nano-super hydrophobic self-cleaning coatings and electrostatic dust removal technology. Build a semi-underground base with a retractable protective cover on the surface. Develop inflexible protective domes and integrate magneto-hydrodynamic sealing technology. Configure sodium-ion bacterial packs and hydrogen foil cells to ensure power supply. Build a controlled ecological life support system to achieve the recycling and regeneration of oxygen, water, and food.
Water resources within mineral is the main source of water on Mars. Hydrated minerals are widely distributed on the surface of Mars. These minerals mainly include layered silicate minerals such as monotameronate and kaolinite, evaporate minerals such as sulfurite and carbonate, and hydrated silicon dioxide. Among them, iron or magnesium layered silicates minerals and aluminum-rich layered silicates mineral are the most widely distributed hydrated minerals on Mars. Method of obtaining. By stirring, mixing, and heating the soil to 500 degrees Celsius while releasing preheat nitrogen gas and carbon dioxide to facilitate the release of water vapor. The water vapor eventually turns into collectible liquid water in the condenser. Purification. The nephron membrane is selected to remove perchlorate. It is fully perfluoride sulfuric acid semi-permeable membrane with high selective for water, which can filter out clean water while ensuring the filtration and transmission speed of water, and has certain chemical tolerance. Biotechnological engineering can also provide support for the purification of molten water. For example, biological products containing perchlorate redoxes can be produced, which decompose perchlorates in water into hydrogen and chlorine gas, thereby achieving the purification purpose. In addition, water containing salt impurities can be electrolyzed to obtain hydrogen and oxygen, which can then be collected and ignited to produce pure water, or by using distillation, reverse osmosis, and electrophoric ultrafiltration technologies, etc.
Another potential challenges of colonization on Mars is the problem of transportation. It is too expensive to transport resources from Earth to Mars for infrastructure manufacture. It actually costs $4,000 to transport 1 kilogram of supplies to low Earth orbit and considerably more to send that kilogram of supplies to Mars. In order to solve these challenges, we should use Martian mineral resources to bring the cost of future exploration down to affordable levels. Mars contains a rich variety of mineral. First of all, the bedrock of Mars is covered by a loose layer of dust, sand, and broken rocks, which contains a kind of mineral called regolith. This can be processed and compressed into bricks for construction purpose. Moreover, basaltic rock is the most common volcanic materials on Mars. It is a suitable material for construction due to its strength and durability. Its flexibility allows Martian basalt to be shaped into different forms. Therefore, it is also possible to use Martian basalt for 3D painting. Thirdly, another valuable resource on Mars is called volcanic ash, which is formed by the breakdown of molten magma. One of the benefits is the surface of Mars is covered with extensive amounts of iron-containing volcanic ash, enhancing its availability. This element, when combined with lime, will exhibit hydraulic gelling abilities. Therefore, it can be used as a binding material to help bind the structure together.
Mars' atmosphere is primarily composed of 95% carbon dioxide, 3% nitrogen, 1.6% argon, and with only 0.13% being oxygen, and the rest being water vapor and carbon monoxide. The oxygen level on Mars is far too low to support human life. Humans requires an oxygen level of 19.5 to 22% to be able to survive. At such a low oxygen level, humans would experience severe hypoxia, leading to loss of consciousness, organ failure, and death within minutes. This makes it another significant challenge that colonization on Mars would have. Leveraging this carbon dioxide dominant atmosphere, the most viable method for oxygen production is the electrolysis of carbon dioxide through the process of solid oxide electrolysis cells. The solid oxide electrolysis cells technique is suitable for Mars because it utilizes materials that are already present and generates minimal energy waste. The process involves heating carbon dioxide in a high temperature of 600 to 1000 degrees Celsius in the electrolyzer, where the chemical balance of carbon dioxide weakens, making it easier for the electric current to split the molecule into oxygen and carbon monoxide. This high temperature operation is critical because it reduces the electrical energy required for the reaction to proceed, cutting down on the electrical energy input needed from power sources. This is essential as power sources like solar panels have limited capacity, so saving energy is essential. The carbon monoxide produced in the process will be discharged back into the atmosphere. This is beneficial because the process utilizes the Mars environment to deal with the byproduct. Since Mars' atmosphere already have carbon monoxide, adding the carbon monoxide produced in this process back into the atmosphere does not pose a risk of accumulating harmful substances on the planet. This also means that no additional complex waste management system is required to handle the byproduct, making this process a practical and sustainable way to produce oxygen on Mars.
Next, I would like to focus on the way we can create electricity on Mars. Nuclear power is the perfect option for early missions because it is a long-lasting, high-power, and reliable energy. Additionally, the waste heat from the reactor can be utilized to power the ISRU reaction. A prime example is the kilopower system being developed at NASA's Glenn Research Center, powering human Mars and Moon settlements. The next best available alternative source of power is solar power, since the numerous solar probes have been launched to Mars. As on most rocky bodies, silicon required for electronics and solar panels is ubiquitous. In Martian regolith silicon, it is hard not to have any rock or regolith without silicon in it. All three metals melting procedures outlined in the second part are available: carbon thermal reduction, hydrogen reduction, and electrolysis of molten effluents. The final choice is wind power. Windmills differ from solar panels in that they work most efficiently during sandstorms and can also work at night. This has the benefit that where there is no solar energy, wind power can be employed as an alternative actuality power source. A major benefit of wind power is that it does not need special materials like silicon or enriched uranium, making it easier to manufacture locally. Another problem people are going to face when they're doing the Mars colonization is the gamma ray. The gamma ray is a type of shortwave electromagnetic radiation with zero rest mass, electric charge, and magnetic moment. It has strong penetrating power and carries high energy, which can easily cause the deoxyribonucleic acid in the cells of organisms to break, thereby leading to gene mutations and might cause death. Several strategies can be adopted to prevent gamma rays on Mars. It mainly includes passive shielding with materials such as water or rocks, as well as active shielding with magnetic fields or advanced materials. In addition, the time spent burned under the Martian regolith and in natural radiation shelters can help reduce exposure to gamma rays. Water and rocks can effectively block gamma rays because they can absorb and scatter radiation. A thick layer of water or molten regolith soil can provide a considerable degree of protection. That is to say, burying the habitat beneath the surface of Mars can provide a natural barrier and reduce exposure to gamma rays, or create an artificial magnetic field similar to the Earth's magnetosphere, which can deflect incident charged particles, and these charged particles can cause radiation. These are the main problem and mainstream solutions that you are highly likely to encounter in Mars colonization. The reasons and significance of Mars colonization lie in exploring the origin of life, seeking future habitats for humans, and responding to potential disasters on Earth.